Okay, cool. So I know I just said my screen sharing will work. It should work. All right, so let me jump over to the book. Uh, oh, and I should get to the right page. Sorry, jump down here. Do you happen to know, here's chapter five, so I'm too far. Oh, there we go, I think. Oh no, I got to go one more chapter. Um, Here we go. Okay, so controlled structures and method dispatch. Let's see. Oh, something that was interesting to me about the beginnings of this chapter that I was going to mention is I was actually going to ask you guys if you've ever learned assembly language of any sort before.
No,
Uh,
not to me. Maybe Nelson.
I've looked at it. I don't, I'm not like super familiar with it.
Got it. I feel like this book kind of, and I don't know for sure what the author's intent is. I kind of feel like to some extent the author almost feels like you already know assembly language because he blasts, I feel like he kind of moves through the first part pretty quickly, which is fine. But I was going to mention let me see if I can find this here. I was going to mention this video game here called Human Resource Machine, where it's basically a video game, but it's like you're writing assembly language in disguise. Unfortunately, so you drag these instructions from the left to the right, and unfortunately, I couldn't find video of the person dragging the instructions around, but you can kind of see the program running. So I was going to recommend this if you just want to have fun and learn assembly language programming. So you can see like this green arrow here is the program counter. There's no stack. So it's kind of like this is kind of more like a register based assembly language where you have 16 registers and input and output, but there's no actual stack, but you do get a program counter. But for like the jumping and branching stuff, see how there's like this jump if zero? That reminded me of the like branch if false that is mentioned in the book. And let's see. And then like here's like a page of some export. Like when you save the game, it actually saves it like this, which is like assembly language. Um, it's like a custom assembly language, but you can kind of see how this looks sort of like the YARV instructions, even though this is a custom assembly language. But anyway, I was just going to point that out. I think it's free, um, but or I think you can play most of it for free. So if you wanted to kind of play a game and learn assembly language at the same time, not even know that you're learning assembly language, I can recommend that game. Yeah,
I'm
so that was something that came to mind.
I'm sort of learning assembly language by other means.
Hmm.
Um, so right now I'm making my way through the x86 manual to figure out the what all the instructions are in binary format and decoding those instructions
Mhm.
using Ruby. So I'm making my way through the move instructions right now. So there's a bunch of variations for the move instructions. Um, I'm a little stuck at one point because negative numbers, it's hard to differentiate like a very big positive number from a negative number
Mhm.
because in binary there's nothing. I mean, it negative number is differentiated by one uh, in the first uh, index of the byte. But that is also, it could be there's nothing in there to say, okay,
Yeah.
this is a signed integer value or an unsigned integer value. Um, I don't know what I'm going to do about that. I think I need to read the manual a little deeper, but yeah, that's that. All of that is to say, yes, I am sort of learning this stuff at a deeper level, and yeah, it's actually more complex than I thought. Well, I
Oh,
mean,
that instruction set is really. I've learned. Well, if you count human resource machine, I've learned three assembly languages, and now
mhm.
if you throw in, I'm learning YARV. I guess that's technically four, but I learned MIPS which is a type of assembly language, and x86. And x86 was way, way, way more confusing than MIPS. So I would say that x86 is a particularly confusing assembly language, in my opinion. Um, for the negative numbers, I think you might not even be able to tell because if I remember correctly, they store them in two's complement, and the first bit is a one, but it's in two's complement, and that allows you to pass. I think when like negative numbers and positive numbers pass through the ALU, they both pass through identically. Like the ALU doesn't know the difference between negative and positive numbers. It just adds them as if they were two positive numbers, and then the code, I think, and I could be wrong about this, I think the code a layer above either interprets it as signed or unsigned, but I think that at the assembly language level, you might actually not be able to tell the difference between the two. Because I think that when it's going through like all the logic gates and stuff, there's not like a branch where it's like, oh, I'm adding a negative and a positive number, do this instead. It just flat out adds both the numbers regardless of whether they're positive or negative.
Yeah.
Um, yeah, that's an interesting one. So you're basically writing your own disassembler, which will come up later in this chapter, which is kind of cool. So you're writing a disassembler, which is kind of cool.
Yeah.
Um, and if I don't know how far we have to go to find it. I'm tempted to just scroll ahead and look for it since we're already talking about this. Well, we'll get to it, but there's like one or two places in this chapter where I think he compiles some code to bytecode and then disassembles the bytecode, and you're basically taking x86 quote unquote bytecode, the binary, and disassembling it into human readable text. So we'll see the same thing in this exact chapter of what you've been up to.
Yeah.
Yeah. Okay.
Well, so yeah, so this is a little bit at a higher level because all this bytecode, is not machine code, and so it can't be sent directly to the processor.
Right.
But at some point, it's got to be converted over to machine code in some level, and we haven't seen that yet, or they haven't talked about it really yet.
Well, I don't think it will be. I know Java does that sometimes. And actually, maybe now you had mentioned YJIT in the last meeting. I actually don't know, but YJIT might produce machine code. I actually don't know. But you don't have to have machine code because you're running it on the virtual machine. So the virtual machine is running a machine code and can actually run the YARV instructions without having to compile it down to machine code. You would have to compile it down to machine code for performance reasons if you wanted to. And I do know Java's just-in-time compiler can do that. It can take Java bytecode and actually compile it to machine code. As far as I know, it doesn't do that, but I actually don't know. Now you have me curious. I kind of wish I had a pen with me because now I kind of want to look into that. But
Well,
yeah,
I mean the even if the bytecode uh, doesn't get translated to machine code directly, the virtual machine has to send out machine code. It has to emit machine code for the CPU to consume. So at some level, and it's not a level that the book might the book might not get into that level, but like, Mats, when he was writing the interpreter or YARV, uh, someone had to do it.
yeah. YARV itself should, for performance reasons, be compiled down to machine code. I believe YARV is written in C, so it is compiled down to machine code.
Hmm.
So the virtual machine itself is absolutely running in machine code. It has to be like you would definitely you wouldn't write it in C and then not compile it to machine code. So
Right, right.
yeah. And then a bunch of instructions, a bunch of the YARV instructions are optimized with C code, which we'll see in certain places. So let me go ahead and jump through here. This stuff reminded me of that human resource machine game. And Nelson, as you're learning x86 and building this disassembler, you must have seen, jump if false, jump if true, and labels. So usually you're jumping with labels instead of numbers. But yeah, uh,
Yeah.
cool. So let me
Yeah, I'm
see.
at a weird place where like I'm learning the actual machine code instructions without actually knowing what a jump does or what a pop does, really.
Oh,
Yeah.
yeah. So a
So
jump, yeah, I can explain that. So do you guys remember that there's a program counter and a stack pointer from the previous
Yeah.
chapters? All the jump pointer is doing, Nelson, is it's clobbering the program counter with a new value. So normally the program counter is like 0, 1. Actually, I don't know where 1 is. But anyway, 2, 3, 5. So there's some missing instructions here, maybe to make this a little more legible. All jump is doing is the program counter. It starts off at 0 and then increments. Jump just basically says whatever is in the program counter, clobber it with 33, which means that now the next instruction to run will be trace. So that's what jump is doing. It's like instead of proceeding from 23 to 25, like instead of incrementing the program counter because we've just completed an instruction, it's going to completely clobber the program counter with a new value.
okay.
And this is going to be, I think we're jumping into a block here, or well, there are no blocks here. So I don't know actually what we're doing here.
Well,
But we are,
it should be it
oh,
should
it's
be
the
the if
if else.
statement.
Yeah, yeah. It's the if
So
else branching.
so in the if this is true, then we put small. So we're gonna not jump anywhere. We're just gonna continue the with the code. But
Ah, yeah.
if it's false, we are gonna jump to the false condition.
Yeah. So that's what's happening. So we're coming through here. I is less than 10 if we're in here. We put S small, like Nelson just said. And then we do not want to put S large. So we need the jump to implement the else. So we've done this, and now we want to jump to here. And this code here is at address 33, which is right here. So we want to change the program counter from 23, instead of going from 23 to 24, we want the program counter to go from 23 to 33 so that we can start executing this code and completely jump past this code. That's what jump is doing. All pop is doing is it's decrementing the stack pointer. So, and I actually took a note because I was going to ask you guys about that pop because it's kind of an interesting thing there. Because it took me a moment to figure out why I think that pop is there. But pop is going to decrement the stack pointer. So you remember that the stack pointer points to the top of the stack.
Hmm.
When you pop, you're moving that stack pointer down so that now if you were to push onto the stack, you're going to overwrite what was there before. It's kind of a way of saying you're done with what's on the top of the stack. You don't need it anymore. It's like you can throw it away. So I actually was going to ask you guys if you guys knew why this pop was here. Or was it the one on, oh, for both of these, the one on 22 and the one on 32? I was going to ask you guys if you'd be able to take a guess at why those pops are there.
It's probably putting small on the stack and large on the stack, and then popping those off.
So what my guess was that this put S here.
Hmm.
I think this is going to put nil on the stack. Do you remember last time, Nelson, you jumped over, or it might have been Newton. Someone jumped over to their IRB session or whatever
Yeah.
and printed out nil. I
Yeah.
think what's happening here is that put S is going to leave nil on the stack just in case we want to do something with it. But the compiler knows we're not doing anything with the nil. So it's just junk on the stack. And I'm guessing we could probably just leave it there. But I think like as a space saving optimization, it's like we just call put S. We know put S is going to leave a nil on the stack, and the code isn't making use of that nil at all. So my best guess is this pop is just throwing away the nil that's the return value of the put S.
Mm.
That's
Yeah.
my guess there.
So I have a question regarding this. Because now I'm confused. Maybe it's because you guys started talking about hardware and then I got confused. Anyway, so we have an if statement here and we've created a new variable. The variable is I. We assign it to an integer which is 0. Yeah.
Mm-hmm. Yeah.
So as per this if statement, we expect the output to be small and then done. Those
Yes.
are the two strings we expect as output. So
Yeah.
when you look at the diagram on the right, you put an object, this is line 2, you put an object 0 onto the stack.
Mm-hmm.
Yeah, and it's a local variable. I think
Yeah.
that's what set local means. Yeah.
Yeah. So
Yeah.
that's those two instructions are implementing the I equals 0.
Yeah.
Yeah.
And then you proceed to trace now, because trace is like the very first instruction. This is line 5. Yeah.
I
And then
actually
after you
don't. Oh, sorry. Go ahead.
mm, and then after putting the variable onto the stack, now you access that variable with get local.
No, I don't think so. I think so. One thing, and I took a note of this, Newton. One thing I find confusing about this assembly language is I do not understand why this is not called push object, because this is pushing an object onto the stack. And so to me, put object is very confusing. I feel like this instruction should be called push object. So I think what happens is we push an object on the stack, and then set local is an instruction that takes the object off the top of the stack, pops it basically. So set local is going to pop an object off the top of the stack and stuff it in this local variable table. And I think the 2 is the slot in the table. And we went, this was part of the last week's
Yeah.
chapter. I think 0 was like how many environments back to go, something like that. But I think 2 was the slot. So we're basically at slot 2 in the local variables table is the local variable I. So we push 0 on the stack because set local pops an object off the stack and puts it in the variable table.
Oh, so
Okay.
so at the start of the program, we're in one context, and then we encounter the if statement, and that sets off a new context. And so it needs a new local table. And so we're we're taking the I from the other context and we're copying it to the new local table that gets created because we encounter the if statement.
I think so. Although
So,
the only thing I don't know is if it's truly because this is a 0 instead of a 1. So I'm a little confused. It almost looks like it's not a new scope. I actually don't know what trace does. And I think this came up last week. And it seems like trace definitely always happens when you start a method or enter a new block. But here we definitely see it when you're entering the if statement. So you could be right. It could be trace is an aspect of setting up a new and you can create variables inside an if statement, right? And I think that in modern versions of Ruby, they're actually local to the if statement, right? I'd have to play with that to actually verify. But yeah, I think you're uh, basically right. The only thing I'm confused about is I don't understand why this isn't a 1 if I is truly like a whole environment backwards. You know what I mean? So I'm confused about that part.
um, okay, according to what I'm understanding, yeah,
So
Oh
there,
yeah, yeah,
mm, I'd I'd stopped at the point at which now you have the second trace.
right here.
Though the fact that this 2 and then the 0, this thing from the local variable table is it's causing issues because personally, the way I'd interpreted it, I thought maybe it was for access of the variable I, because we need it for the next instruction.
That's this. That's this
Yeah,
here.
yeah,
Yeah. This is so get local is saying go to the local variable table, find the entry in 2 and push it onto the stack.
yeah.
Yeah. So this is
And then
fetching I and sticking on the
mm,
stack.
and then we put another object onto the stack, which is 10, and that
Right.
makes sense. Yeah. And then following that, I see that we have, I think, a method call here. No, 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 no,
Yes,
no.
it is. It's the less than method,
Oh, yeah. So we have a method call there.
which is right here.
Yeah.
Yeah.
Okay. It kind of
Yeah.
makes sense. Mm.
And because that one other thing I've noticed here, because Ruby methods all have receivers, it's kind of interesting. But you can, in these simple method calls, it looks like you can take this argc number and add 1 to it. And that's the number of things that are going to get popped off the stack by this operation. So we push I onto the stack here. with the get local. We push 10 onto the stack here, and then we call opt-lt, which takes one argument. This is going to pop two values off the stack, the 0 that was stored in I and the 10 that we put directly on the stack because it was an integer literal.
Yeah.
And it's going to do a less than operation. And it looks like that's going to put a true or a false on the stack. So it pops off the 0, it pops off the 10, and then it's going to push true onto the stack.
Yeah, but
And
another question I have is that why isn't this output ending? Because ideally this thing should give two strings, which is small and done.
yeah,
But then where's the large coming in? The large shouldn't be part of the output, but I'm saying it's being pushed onto the stack as well.
which one?
The string large, line 28.
Large.
Oh,
Yeah.
because that instruction implements this code path. So
Oh,
it has to be in there because
yeah,
if I were 11, then we would want to print out put S and done. So
yeah, yeah,
it will never. So we're never going to execute this instruction. But and you know what? If it could be that in Ruby 3.4, if we wrote this code, it's possible that Yarv might not put these instructions in here. It might be smart enough to realize this is unreachable by this program. Therefore, I'm not even going to output the instructions. We just don't know if it would try to optimize that or not. But I think the reason this is here is that it's just a very naive compilation of this program where the compiler just isn't smart enough to know by
yeah.
analyzing the program that we don't have to run this. So it puts it in the output and then we jump over it so that it doesn't happen.
Okay.
Yeah, we jump over it here. This jump 33, when we hit this at the end of printing out small, this jump 33 is going to jump us all the way to here. And then we're going to keep executing 33, 35, 36, 38, 40. I guess leave is like the end of the program here, but I think it also happens at the end of methods. And I actually don't know if it happens at the end of blocks or not. But yeah, we jump over it. So this jump 33, so this is in the output. It doesn't technically be in the output, but need to be in the output, but the compiler doesn't know that. So it's not optimizing it out, but it is putting a jump statement to skip it. So it'll never run. Does that make
Okay.
sense, Newton?
Yeah, yeah.
Yeah. You have me now interested in actually compiling this with the modern version of Ruby because you're right, that code is unreachable. Would Yarv in 3.4 be smart enough to be like, I don't even need to create the
Yeah.
if statement? And I actually don't know. I have no clue if it would or not. Yeah. Okay, cool. Oh, I had another question, but maybe in the interest of time, we should move on. I'm curious what the heck is at 0 and 1? Because I've noticed in the book, whenever we're doing these variable tables, it looks like it actually starts, it kind of likes to work backwards. So it's like if there's 4 local variables or like 3 local variables, it'll be 4, 3, and 2. But it just has me kind of wondering what's at 0 and 1. I don't know if there's like special values at 0 and 1 or not. But maybe I have no clue what the answer to that is.
Also, another interesting thing that came up in my mind was the author mentions how Ruby would compile the unless kind of if statement. And then he also talks about the while kind of if statement. But then I don't know if the same kind of logic applies for case statements.
Case statements, that's a good question. So case statements, I think, are going to look way more complicated than this because it has to call the equals 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 operator. I don't know if you remember that. But case statement, I think it's going to have a whole bunch of jumps and branches, but it's probably has these opt method calls for equals equals equals, which I don't know what that instruction would be called. But yeah, my guess is that would look like a big jump table in the code. that
Yeah,
you can,
lots of
yeah,
jumps. Yeah.
yeah, lots of jumps and lots of calls to equals equals equals. Um,
Okay,
yeah,
so that was the question.
cool.
I have an answer for you about the current behavior, and the current behavior also uh, includes
Hmm.
the unreachable block.
Got it. Okay. You know
Mm.
why that might be, by the way? And I don't know this. I would have to try this because maybe you would get an error. Well, it could be two reasons. It could just be that no one has implemented it, that optimization. The other could be how does the Ruby runtime know that we have not overridden this less than method? You know what I mean? Like we might be able to override this less than method to either always return true or always return false. Although I guess if it did that, it wouldn't be able to put output this opt LT. So that can't be the explanation. So it could actually just be that no one's done the work yet to try to optimize that. For all I know, that it's just too hard to like be certain that you're not introducing a bug in the runtime by trying to cut this out. That's cool though. So you did you just do that dot disassem
Yeah,
call? Oh, that's
Ruby
cool.
Ruby VM instruction sequence dot compile the code and then dot disassem.
That's cool. So it doesn't optimize that out. This is the kind of thing that like a C compiler probably would if you were to do this in C, Nelson, and then disassemble it with the code you're writing, there's a good chance it wouldn't even put s large in the output because a lot of work has gone into those compilers.
Yeah, that thing is confusing because I thought the entire point of these new compilers was to only compile what's needed. So, but anyway, I'll try to read more about that
Yeah, I
maybe.
think the hard part there, I think, Newton, is just that it's hard to safely know what is or is not needed from the compiler designer's point of view. That it's just kind of scary because um, if you get it wrong, you you break the language. So I
Yeah.
think, but yes, that would be an optimization of sorts. So cool.
That is an optimization that happens, but it happens at a processor level because when the processor is trying to do branch prediction, it'll
Mm.
just use whatever the last run was. It'll just use that path. So if it's always going to, and this code is always going to be less than 10, it's always going to branch predict the first path, the true path.
So that could be another. It could be that someone wrote that and then benchmarked it and didn't get any performance benefit. So because of magic, like what Nelson just mentioned, so maybe because of magic in the processor, um, the compiler designers were like, they benchmarked it, there was no benefit, and they were like, let's just go with the simpler implementation. For all I know, I'm totally guessing. That is true. There's a lot of magic that can happen at the processor level these days. Um, I
Um,
sometimes see like security incidents related to that stuff and whatever, but yeah.
the other question that you had was about why, it picks up the two. Like, why is
Mhm.
there a two there? What's before two?
Yeah,
And what's before two is probably going to be the value of self.
that could be, yeah, self. I wonder what would be at zero, maybe nothing. I don't know. Yeah. Self would make sense though. Interesting. Um, cool. So let me see. So I didn't have any other notes until page 87. Let's see. So here we have like a branching diagram. It's kind of showing you. Um, so actually, Newton, if we look here, we can see the large is in this like chunk here. Like they've broken it up into chunks. We come down here, we branch to this block, which then jumps to here.
Last
Um,
one.
yeah, one thing that's kind of confusing is I actually don't know what this arrow here represents. I guess it's not the flow. Um, this arrow here actually confuses me because we have the jump here. I probably would have left this arrow out. I mean, this is what would happen if you didn't jump. It would continue on. But yeah.
Oh, I think the long arrows are related to what is returned to you depending on the condition, and then the shorter ones are related to how it's compiled all at
Okay.
once. Yeah.
Okay. So let's see. Okay, so then we're talking about jumping from scopes. Ah, this was interesting. This was the stuff with the catch tables. I'd never thought about how that works before. Um, and so this was actually really interesting to me. One thing I did find confusing, at least at first, by the way, was this that there were two blocks here. This actually, I think I finally figured out what the author was going for, but I think at first the fact that there were two different blocks here actually confused me. I think one is the outer scope and one is the inner scope, but I didn't understand that at first. I think like Yarv output two different sets of instructions, one for the block and one for the outer scope, and I think I was confused by that at first. Um,
Yeah, I think those are two. Um, I think you're right. But in the last chapter, they had a name. It's like oh, I've forgotten the name already. But it was the thing on the right hand side. It was the a different sort of stack. Ruby control frame.
oh yeah, okay. So
So
these are
it's
the
a
two
it's a
different.
different Ruby control frame.
Yeah. Okay. Cool. Alrighty. Um, one thing that in my opinion, that would actually help if the author did would be, and I understand that there's limited room. I actually feel if he would walk through what's happening to the program counter and the stack pointer, like if he would like just kind of show those step by step as moving through here, it would take up a lot of space, but I think it would help reduce confusion. And I was reminded of that because I remember last week I kind of wanted to see both stacks because remember last week's was there's two different stacks. One is the stack that the data is on, the other is the stack of control frames. So these frames are on one stack, and then get local is get local pushes onto a totally different stack. Um, so yeah,
You
okay.
know, I have seen that before, but not in a book. I've seen that in a virtual machine that was running 8086 code, and so you could see all the registers, you could see all the flags, and the anything that was in memory, and you could step through it, one step at a time, and it does help understand that. That sounds like a good tool that like someone who's developing Yarv would need to have or would want to have. I don't know if it exists or not, but yeah, that sounds.
Yeah, that's a good point. So if I actually just jump back over to this video game real quick,
Hmm.
when you're playing this game, you can see the contents of all the registers changing over time, and you can see which instruction you're pointing at and how they jump around. So you actually see the program counter moving and the state of the registers changing. That reminds me of like what you were just discussing as a learning aid for assembly language. Um, but this book isn't kind of walking through that, and it must just be to save space because it would take up because that's a video, and it sounds like what you're referring to is animated, right, Nelson?
Yeah, I mean it's a terminal application that just shows you. You can click S to step through the code, and it just shows
Right.
you everything.
Got it. Yeah. So it's like a debugger. And
Yeah.
I guess when you're in the book medium, there's not a time component. So you'd have to draw the contents for each instruction to
Hmm.
communicate it. And I guess the author must have just made a decision that that would take up too much space or be confusing.
Yeah.
Um, but yeah, here
It
we have oh, go ahead.
it might be time to switch to the other meeting.
Oh, okay.
So I'll
Yeah.
see you on the other call.
Okay, cool.
Okay.
All right, dropping off.